I'd like to introduce the second speaker, Professor Alessandro De Luca. So yes, so please go ahead.
Okay. Thank you. So thanks to Tamin and Stefano for inviting me to this very nice event. So I will talk today about safe control of physical human-robot interaction. You have heard before in these 2 days about HRI, cognitive more, here also a bit physical. So I will talk about the physical part and, in fact, only part of it. So over the years, when the robot starts going out of the cages of industries in homes or also in service application, there has been many attempts to make the behavior of a robot safe. So we can list here mechanical design of lightweight arms. There are a few examples below. Inclusion of compliance in the actuation, even variable stiffness actuation, and along the structure if you want to have a soft structure. And by and large, all these activities were moving the traditional way of looking at robots, like position control, high payload, high precision, to a more compliant behavior, more natural behavior. Indeed, if you want to live in an environment which is not structured, you need exteroceptive sensor on board or in the environment. If you want to touch the environment with a robot or a human, and in this case, you need a proximity or tactile sensor and force source measurement. You can integrate all of this in your system. And another important fact is the planning of legible motion. This is an activity done very well by CNRS LAS, so that the human can understand what the robot is doing. And this is what I'm going to talk today, motion interaction control schemes. Okay, of course, there are techniques that include safety constraint and safety objective. I will do, let's say, conventional, what is the name, engineering stuff, hopefully good enough for solving our problems. And I must say also that over the years, there has been also advances in the definition of safety standards which allow the robot to interact more closely with humans. And the Safari activity produces also some contribution on that. So over the year, we've set up a control architecture handling 3 different problems which we are safety related, and for us, they are really control problems. So first of all, safety is very important, which for me means being able to detect collision as soon as possible and to isolate which link has collided with the environment, and then to activate a reaction of different kinds. And we would like to do this without the use of external sensing, of extra sensor. Only the position sensor could be used in this case. Now, the second aspect is not going. Okay, sorry. There's some delay. Okay. So the second aspect is what we call coexistence. So 90% of the application of collaborative robots in the current industry, at least in Italy, they are concerned with coexistence. So robot and human sharing a workspace, interacting very little, so pick-and-place objects that are left by the robot and taken by the human or something like that. So for doing this, we need external sensing because we need to measure distances, and so do collision avoidance in the traditional way. So we call this coexistence. Of course, if we are focused on coexistence, we don't have to forget safety. So in this sense, we have a hierarchical structure of architecture, because the next step is collaboration. When we really exchange forces, and we'll have to do this in a controlled way with the environment, with the human. Okay, and here, with or without using sensor, as I like to sing, with or without you. And all this stuff has been then set up into a layered control architecture. And let's see some examples. For instance, for coexistence, this is Fabrizio Flacco. Unfortunately, he's no longer with us. Doing some experiment where the robot is doing a cyclic task in the Cartesian world, and we use a Kinect. Sometimes we use 2 Kinect to limit the gray zone in the workspace, and we do distance computation in the sensor space, so we don't build point clouds, and this is why we are going quite fast, and of course we update the control law every 1 millisecond on a KUKA. So now if you want to see the integration of this, sorry, okay, with collaboration. Here is again, you can hold the end effector and control extended forces at this type. Then you give a target, so for instance, doing a gesture or with a voice command, and the robot is going to this target because it wants to collaborate, but still coexistence is important, so all other parts of the human body are avoided. And you can see this is done with the human body, but with any other obstacle in the environment. And I think that the last part of this short video is more impressive because Fabrizio is holding the tip and is pushing against his arm, but of course the robot becomes stiffer and stiffer because coexistence should be preserved and safety as well. So now talking about safety in 2017, after many years of collaboration, we finally published this paper with Sami and Aline on TRO, giving this collision event pipeline. So safety here is in this pipeline, detection and isolation and possible identification of the exchanged force. Indeed, the part which is related to coexistence is before, and collaboration comes at the end when the robots should react. And sometimes it just stops, sometimes it starts an active collaboration with the human. So this is the only mathematical slide that I have. Robot dynamics is known to everybody. Tau C is the joint torque resulting from a collision everywhere at any time along the structure of the robot. And we use two physically motivated signals, the total energy of the system and the generalized momentum. Now, you can write how these two quantities evolve. One is a scalar, one is a vector. And based on this evolution, you can design computable signals that you use to monitor collision. In fact, the sigma is a scalar, is used for collision detection, and rho is a vector residual, which is used also for isolation. And in fact, they are sensitive, their evolution is sensitive to collision. So with this, you can set up a behavior of the robot. You have a collision monitor always active. You can detect or isolate. You can use both signals at the same time. When you overcome some threshold, the collision is detected, and then you activate reaction strategies. And there are many reaction strategies that you can do. And of course, the nice things about these signals is that if the contact is removed, their signals come back to zero. So you can really continuously monitoring a succession of contacts with the environment. So here are the first implementation of this type of idea. Okay, we're here. Too fast. I should be. Okay, so the first one were at DLR when I was during my sabbatical, and these are the first impact that you had, and with two different types of reaction. One is an admittance mode, so the reaction, the residual is converted into a command in the Cartesian space, velocity command. The reflex reaction instead is a torque-controlled reaction. And of course, you are familiar with this famous experiment. Sami was very confident about the software. And you can use the same techniques to evaluate. So keep the same path, but scaling the trajectory. And if you push too hard, then you have a reflex and the system goes away. So another thing which is important is to discriminate whether the contact is intentional or not. Because if it's intentional, then it may lead to a collaboration phase. If it's instead undesired, it is a collision, and the robot should simply stop or react as before. And we did that by simply filtering in different way the residual signal. So we have a high band filter and a low band filter, and we are able to discriminate collision, the robot stops and then resumes its operation, or collaboration. So this is a soft contact, and from there on, we are controlling the exchanged forces no matter where you're touching the robot. This is very important. Okay, so, but are we really regulating the exchanged forces? This is very important. This is a result by, in 2015, at ICRA 2015, and you can see that we set a 15 Newton in that direction, and the robot keep contact if you're pushing or if you're pushing too little, and regulate the exchanged forces. Once you have this estimation, you can implement any interaction controller you wish: admittance control, impedance control, hybrid force velocity control. As you know, I mean, if you want to do a joint compliance control or a Cartesian compliance control in reaction to some forces applied anywhere, you don't need to estimate the force, okay? But if you want to achieve impedance control, again, here, okay, then you need either a joint torque sensor or a force torque sensor, because you have to modify the apparent mass of the system. So in our case, we don't have this force sensing. We are estimating force, and we're reacting to this estimated force as if it was measured. And this could happen at any point in the structure without the need of tactile sensor or other external sensing. So these are some examples of this admittance control. So we are using a velocity command for the robot or a torque control. And of course, you can also play around with this residual. Here we combine the use of residual with force torque sensing, and we are able to discriminate the type of interaction. So this is mimicking a manual polishing on the end effector, while the reconfiguration in orientation is done by just pushing, so a kinesthetic command. Or you can use redundancy of your system so that you react to the contact, but without relaxing the task. If the contact is too hard, then you relax the task, and so you can achieve a hierarchy. Now, I'm almost done. So when things happens at distal, so when a contact happens at the 6th or 7th joint, link, sorry, then you can use the residual also to estimate the force. So without any information from outside saying where you have this contact. Unfortunately, you can't always get what you want, so there are cases in which you cannot do this. And this is very clear from this simple example. If you hit a 3R planar robot on the first link, you can only estimate the normal force to the link if you know the contact point. If you interact at the second link, then you can estimate both components of the force, but you should know still the contact port. If you go to the third link, then you can really recover the whole information. And if you're working now on the proximal link, so the one close to the base, then you should use dynamic information. And we implemented the contact particle filters, which was proposed by Rusted Drake. So it's a data-driven system. And you can really identify also the contact point, even if you're contacting the robot at the base. Indeed, if you have extra sensor, like with the SARA robot, so if you have also force torque sensor mounted at the base, you can do a lot of nice things. But we try to be, say, conservative in the use of hardware. So summarizing, so far, we have presented the physically motivated method for detecting collision. I call it sensorless because we are not using extra sensor. And these methods can be applied to a variety of robot systems, so including joint elasticity, link flexibility, humanoids, floating-based system, UAVs, and so on. And it's also can be applied, and we did it, in close control architecture of industrial robots. And I consider this just another brick in the wall. So just a simple element that can be used together with some other method. In fact, in the near future, I foresee very simply the integration of data-driven and model-based method. These are model-based methods that can be used in data-driven system and vice versa. And also, I've talked about physical, but cognitive is equally important. Multimodal communication in different ways, also very important here. And human intention prediction, this is a very active field. This depends on the context. So anticipative action would provide more, let's say, ergonomic behavior with the human. And finally, robot learning. Of course, when you learn in human-robot interaction, the human should be in the loop, and this is very critical, I mean, time-consuming. Thank you.
Thank you very much. Any question?